All right, friends. So we're on 3C.11. On 3C.11, we are continuing to analyze log functions, which again should feel somewhat like a review because it's information we already know. So if you look up here, we talked about the inverse relationship. Um, Inverse relationship between log and exponential, and therefore all their characteristics are going to be the inverse as well. So their domain and range, all those things are going to change. So when you're looking at them, when you're looking at the log function, you want to keep in mind that you already know everything you need to know about it as long as you know an exponential function. Okay. The log general form is a log base b of x. Each piece is called has a role. Your a is your coefficient, your b is your base, your x is your argument. Okay. Your domain is from 0 to infinity. Your range is from negative infinity to infinity. When your a is greater than 0 and your b is greater than 1, then you're going to have an increasing log from left to right. If your a is less than 0 and your b is greater than 1, you're going to have a decreasing log from left to right. Just like linear functions, log functions are either always increasing or always decreasing. Okay. And because of that, there are no relative max or mins, aka no relative extrema. The only time you'll get that is if I tell you to only look at a specific interval. And then let's talk about whether it's concave up versus concave down. They're either going to be one or the other, obviously, right? They're either going to be always concaved up or concave down. Bless you. Um, the key thing here is that they do not have any points of inflection. So log functions do not have any points of inflection. Okay. Their end behavior. Your end behavior is going to be as x goes to positive infinity, y is doing what? Y is going to positive infinity. As x goes towards, we're not going to go negative infinity, but as x goes towards 0 from the right, your y values are going to go to negative infinity. Okay. That's the biggest difference is that your x value isn't going forever to negative infinity. Your x is approaching 0 from the right. Okay. Up next is those attributes. So knowing that, do you feel confident or comfortable being able to identify the limits and behavior of the given function? Maybe, hope so. I think so. I believe in you. Okay. So let's talk about what they are. So on the first one, we're reading this. The limit as f of x goes to 0 from the right would be what? What is the function doing? It's forever decreasing. So it's heading towards negative infinity. Okay, so now we're going to write the right-hand limit. I don't think I made these lines very big. We're going to make it fit. So the limit as x goes towards positive infinity, that's a weird infinity, but we're going to let her make it. What is f of x doing? F of x equals positive infinity. All right. Okay, so again, this time when we're describing the left, we're approaching that asymptote. And she has a key. You're approaching that asymptote. So you have the limit as x goes towards 0 from the right. F of x equals I saw you. It's going to be toward positive infinity. And then the limit as x goes to positive infinity, f of x is doing what? Decreasing. So therefore, it's going to be negative infinity. Now, graphically, when we look at this, it's easy. We're looking at a graph. What if you're just given the equation on a non-calculator? Given the equation on a non-calculator means you have to pay attention to what your A is. If your A is greater than 1, then it's going to be an increasing situation. If your A is if your A is less than 1, then it's going to be 0, I'm sorry, decreasing situation. So when we look at our A value, what is our A value? 2. So A equals 2, which is greater than 1. So I know that my function is going, so even without the graph, you should be able to analyze what's happening because of what your A value is doing. Does that make sense? So this behavior would be the same as this guy. Uh-oh. Because I don't want to write it twice. Your B also comes into play because if your B is a fraction, then that in itself tells you that you're decreasing, right? All right. Next is our concavity. So whether we're concaved up or concave down, which literally, can you tell me when I'm this? Can you tell me when I'm that? Can you tell me when I'm this? Can you tell me when I'm that? Does that make sense? All right. So let's go through our concavity. So we're just circling. On the first one, are we concave up or are we concave down? We are concave on the first one. We are concaved up. We are but what is our function doing? Decreasing. Does that make sense? Okay. On the second one, what are we doing? And what is the function doing? What is this one doing? Okay, what do we need to pay attention to? The A, and our A is what? Our A is negative, which means that it's going to be a decreasing situation. Does that make sense? All right, so what are we doing? So it's same as A, concave up, and it is decreasing. Okay, how do we feel about analyzing concavity? Doable? All right, chugging along. Let's talk about it in tables because all representations have to come into play. So now we're at tables. Being able to identify the log functions based on the table behavior. We talked about this yesterday. And what was the rule for log functions? Not yesterday, you know what I meant. Perfect. By a constant. There you go. So your x has a multiplicative change, right? Meaning that I am multiplying by something to get from one to the next. Your y has an additive change, which means I'm adding the same value to get from one to next. This is when they are equally spaced apart. Does that make sense? So if I'm looking at this chart and knowing those rules, should I be able to work backwards to fill in what's missing? All right, so using yesterday's knowledge and all you know, you're going to go work at your tables and you're going to find the value of each K in each table. You're finding this missing value, and this missing value. All right, and go. All right, friends, what did we get for our first K value? You're geniuses. I knew it. All right, second K value. Oh my gosh. Who taught y'all? Third K value. How do we do the third? Did anyone try to figure out what the pattern was or if they were increasing or decreasing the same? Okay. So let's start. How did you get 11? Okay. Sort of? No. We're gonna give it a shot. All right. So remember, the deal is that they have to be multiplying by the same value. So first of all, I got to figure out what is it being multiplied by, which means that the opposite of multiplication is what? Division. So to figure out what is the pattern that I'm following, I'm going to use division. If the pattern isn't equal, then that tells me that it may not be a log model. So when you're doing this, I need to figure out 4 to 5. That's going to be 5 by divided by 4. That's 1.25. Let's check 7 divided by 5. What is that? Not the same. That pattern isn't existing yet, right? Because that pattern isn't existing, even though this one is adding 10, minus 10, minus 10, minus 10, minus 10. These are not equally spaced apart. Yes? So does this represent a log function? No, this did not represent a log function. Remember, they have to be equal. It has to be the same ratio all the way down. And if that ratio is not the same, yeah, we can say this is 11, but that's a different pattern that's following. So I would say, yes, good job, but is it a log? No. But yes, good on your pattern. All right. And then what about here? How do we do about the e's or feel about the e's? Not good. All right. When you are subtracting exponentials, what does that mean you're doing with the exponentials? I mean, dividing. What does that mean you're doing? I said the word that I need you to say. Subtracting. When you're dividing exponentials, you're subtracting their power. So if I have e to the 10 divided by e to the 7, that's going to equal e to the 3. So e to the 3 is what I'm multiplying by to get from one to the next. Does that make sense? So on this one, it was this times e to the 3. So from here to here, I'm going to do e times e to the 3, which just makes this what? E to the 4. So k equals e to the 4. All right. Does that make sense? I'm trying to think though. Oh, I didn't write it. But yes, k is the 11 is 11. It won't. And we could manipulate this. It just wouldn't be a log. It would be a transform log. Does that make sense? So it's a meaning that even though the pattern isn't here, it technically could be a log, but it's a log that has been shifted. So like there's a +1 inside, which is making that throwing it off. Does that make sense? Like the log has been shifted. So it has a transformation, which makes it not follow the traditional rule. Yeah, but it is K to the 11. So, all right. Domain and range. So when you're finding the domain and range of a log function, you're just analyzing it as whether it's shifted left or right. You are expected to be able to identify the domain and range without a calculator for a log transformation based on its attributes. Okay. So it would appear more so on a non-calculator part of test than a calculator part of test because you're supposed to understand the attributes and what the attributes do to the function. Does that make sense? If it doesn't, then let's pretend that it does. All right, so let's look at the first one. So the first one, we are determining is it increasing, decreasing, and where's your vertical asymptote? So our VA is normally when you're adding something on. Currently, we're adding nothing. So therefore, our vertical asymptote is still at x equal 0. Does that make sense? No, I just add parentheses. Not there. Erase, erase. Pretend the 3 is not in the parentheses, guys. It's supposed to be there. I can't even make you pretend. It's gonna bother me. There we go. All right, it has to have something with our x. That's our vertical asymptote. So if there's nothing there, guess what? We haven't moved. So therefore, our domain is still affected at starts at 0. Does that make sense? So our domain is from parentheses 0 to infinity. And I know it's going towards infinity because it's going forever to the right. And just like exponential, what's going to be your range? Your range is going to always be what? Negative infinity, positive infinity. On exponentials, it's your domain that's all real numbers. On logs, it's your range that's all real numbers. Make sense? All right. So moving on B, again, you're looking and seeing, is there anything with your x? Is there anything with our x? Yes. So now our vertical asymptote has changed. Our VA is now at what? 3, because our x is a liar, so don't fall for it. It's not at -3, it's at positive 3. So now our domain starts at and continues on to positive infinity. I'm just going to write all real numbers stuff, like trying to keep drawing my struggling infinities. Okay. C is an example of where you are not in you're not in standard form. Because this is not in standard form, before I do anything, I have to factor out its leading coefficient. Meaning that I have 2x plus 3, and I'm going to divide out 2, which is my leading coefficient. So now I'm left with 2 parentheses x plus 3 halves. This is what's inside of my log. This is my argument. Now that I see what's inside of my argument, has my vertical asymptote moved? Yes, and it's where? -3 halves. Good job. Our x's are what? Liars. So therefore, our domain starts at -3 halves and continues to infinity. And our range will forever be all real numbers. Got it? Are you comfortable seeing the domain and range in equation form? Okay. Remember that it has to be in standard form, which means that your x has to have a coefficient of 1. If your x doesn't have a coefficient of 1, you have to factor out that leading coefficient so you can find your real asymptote. Capiche? All right, that is 2C.11.